Suppose m is a positive integer. Prove that for all integers a, b, c, and d, if a is congruent to c mod m and b is congruent to d mod m, then a plus b is congruent to c plus d, and a times b is congruent to c times d. Alright, so these are some standard properties in modular arithmetic. And let's write down an example first so you can see what it's all about. So I need a congruent to c mod m. So I could take, for example, 1 congruent to 7 mod 3. Remember, that just means the difference between these two integers is divisible by 3, okay? Which it certainly is. Another way to think about it is that these two integers have the same remainder under division by 3. Right? They both have a remainder of 1. Okay, another example would be 5 congruent to 8 mod 3. Right, so that can be my b congruent to d mod m. And again, the difference of these is certainly divisible by 3. They also have the same remainder under division by 3. They both have a remainder of 2. Okay. All right, so we start out with those two, and basically what this says is that we can add these equivalences or we can multiply them, and it's still true. So if we were to add them, we would get, let's see, 1 plus 5 should be congruent to 7 plus 8 mod the same m, right, 3. And that's true because 6 is indeed congruent to 15 mod 3. Right, their difference is 9. Or you can say they both have a remainder of 0 under division by 3. So this is sort of remainder arithmetic. It's basically saying, if you add something with a remainder of 1 to something with a remainder of 2, you get something with a remainder of 0. And same thing over on this side. All right, then what about this multiplication one? Well, that would be 1 times 5 should be congruent to 7 times 8 mod 3. This one might not be quite as clear as the first one, maybe a little more surprising, but it still works. In this case, it says that 5 is congruent to, congruent to 56 mod 3. Okay. And let's see, the difference between those guys is 51, which is, I believe, 17 times 3. So that's true statement. So let's see how we could prove this in general. Okay. We let a, b, c, d. Okay, well, we're given that m is an integer, and then we'll let a, b, c, d be arbitrary integers. And we will, moreover, do direct proof. So we'll suppose that we have a congruent to c and b congruent to d. And then we have a couple things to prove. The sum of the equivalences and the product. All right, so those are two separate things to prove. We begin by writing out the definition of what it means for these guys to be congruent mod m. It just means that m divides the difference. So that gives us those two statements. And same thing over here. Okay, and then for m to divide a minus c means that there exists some integer k such that a minus c is k times m, right? And similarly for the next one, and I'm going to be careful to use a different letter L there because there's no reason those have to be the same. Bring down my goals, and now I can probably do some existential instantiation, which gives me a k naught and z up here and an L naught and z there. I'll gather those together here. And then these two statements with k naught and L naught. Okay, well, we're trying to find out about sort of, well, a plus b and also c plus d, right? So it might be a good idea to solve these equations for a and b. And then, in the meantime, okay, let's write out what we're trying to show here. Right? These divisibility statements basically mean that we have an h and a j, such that these differences are h times m and j times m. Okay, and now to get our a plus b, we can just add these two equations. Okay, and we get that, and we're also going to have an a times b, right? And for that, we would multiply the left sides and the right sides to get this. And if we just rearrange terms a little bit, if we sort of bring the c and the d together, right, because we're looking for a c plus d, then we bring the m terms together and factor out an m, we get this for the sum. And with the product, if we just expand this out, we get a cd term with no m in it. And then the other three terms you get from the distributive property or foiling, they all have at least one m in them. And so we can factor that m out there. And okay, finally, we're trying to find out about a plus b minus c plus d and ab minus cd. So if we just subtract the appropriate thing from each side, we get these two new equations. And this is really what we want, right? Because we have that this difference is some integer multiple of m, and this difference is also some integer multiple of m. So we just have to maybe convince ourselves that these things in parentheses, k naught plus l naught, and this mess down here, that those are integers. And that follows because, well, all these letters are themselves integers, and all we're doing is adding and multiplying them. So we'll still have integers. Okay. And so those two statements together give us the first goal, and these two down here give us the second goal. All right, so let's write up the proof. Like I mentioned in the beginning, we're supposed to prove this for all a, b, c, d, so we'll let a, b, c, d be arbitrary integers, and then we're going to suppose that we have these two congruences to begin with. Okay, and then before we worry too much about the goals, I'm going to go ahead and just sort of boil down the definitions here. Okay, so say this means that m divides a minus c, and m divides b minus d. Okay, and from that, well, what's the definition of that? We say, in other words, there exist integers k naught and l naught such that a minus c equals k naught m and b minus d equals l naught m. Okay. So where are we so far? We let these guys be arbitrary. We brought over our new goals, and we did definition here of the congruence, and then we did definition of m dividing these things to get here, and existential instantiation got us to these statements. Okay, so so far all that's going to be useful for both of our goals. And then maybe in the next step we can go ahead and mention now as well that we're just going to solve for the a and the b. So I'll say solving for a and b, we get, or we obtain, a equals c plus k naught m, and b equals d plus l naught m. Okay, great. And now we start thinking about our goals, right? So so I say first we're going to prove a plus b congruent to c plus d. All right, that was this one up here, which was always the first one we were listing, which was this guy. And we're trying to find out about a plus b minus c plus d. So that's when we took these equations and added them up and simplified and eventually got what we wanted. Okay, a plus b minus c plus d. So okay, first we proved this. Let me say what we did. So adding the expressions for a and b, we obtain. So what does this look like? A plus b, I'm just sort of copying what I have over here. A plus b is equal to c plus k naught times m, and the b became d plus l naught. Oops. D plus l naught m. And then let me just go to the next line and continue with that. The next thing I wanted was I'm going to group together the c plus d and the other terms, k naught plus l naught with an m factored out. And actually, maybe I'll just stop there for now on that line and throw in a sentence here. So therefore, oops. therefore, my last equation, right, so sort of subtracting c plus d from each side, a plus b minus c plus d is equal to k naught plus L naught m, and that's what we want, right? So that, together with the fact that k naught plus L naught is in z, maybe I should mention that, right? Let's say, oh, come back here. Okay, we'll get this. So I'll say because k naught plus L naught is an integer, it follows that m does divide a plus b minus c plus d. Okay. Right, so we took these two statements to get that one, which took us up to one of our goals. Okay. And now we got to do the multiplication one, which is going to be quite similar. So we'll breeze through this. So multiplying this time the expressions for a and b, we obtain let's see, we had a times b equals c plus k naught m times d plus L naught m, and put my alignment marker in here. Okay, and we multiply that out, and then separate terms and factor. We eventually got cd plus cl naught plus k naught d plus k naught L naught m, all that times m. Okay, so we can say, therefore, AB minus CD is equal to this big mess here, which I can copy and paste. Okay, and I'll say because this big factor here is an integer, it follows that m divides AB minus CD. Okay, which gives us our other goal that, what was it up here? That, right here, AB congruent to CD mod m. Okay, so that was just combining all this stuff down here to eventually get this, which was the definition of that, which was this statement up here. And that finishes our proof.